Good morning. So today what I'm going to try to do is give us a little bit of an introduction into a couple of different things, which are covered mostly in Chapter 13. One is the motherboard itself and what all of these different switches and jumpers and pins actually do. The other is DMMs, digital multimeters, and how we can use them for our different projects. And ultimately, I'm going to put these two together here. We're going to use a DMM to actually help us characterize this board once I get through the basic explanations of what it actually is and what it actually does. So let's just zoom in on the board first. I'm going to move this meter out of the way. And we'll get in here pretty high. Okay. The PRT motherboard. Right off the bat, most prominently you'll see these two switches. Okay, this switch here turns on and off system power. This is the switch that's going to, when it's hooked to batteries especially, is going to turn on and off the processor, as well as turn on and off this center row of pins here. Okay, now this switch essentially turns on and off the left side of the board, this side of the board, and all it really does is turn it on and off this center row of pins. So let's talk a bit about the pins. The pins, you can see there are three separate columns of pins. All the inner pins, well, all the inner pins with the exception of this very top one right here. Okay, so this pin all the way through this pin are connected directly to I/O on your teensy. So recall, if you had the card, which is a little bit washed out in this, you can see that it actually hooks up to pins 23 through 13. Okay, so these male pins go 23 through 13. This pin right here, this very last pin at the top, which sits alone by itself, is actually a direct connection to the 3.3 volt power supply. Okay, so we can use that to power an external 3.3 volt device. The entire center row of pins is going to be your voltage out. Okay, so this is either going to be 3.3 volts or 5 volts. You can select the voltage of this entire set of pins by choosing this jumper here, which you can see is currently set on the right side, the right two pins, which sets it at the 5 volts, which you can barely see in focus here. If I had moved this jumper to the inner two pins, it would be set at 3.3 volts. I should say that the 5 volt supply either comes from your USB cable, okay, or if you're running on batteries, it'll be provided by this 2 amp voltage regulator. All right. The highest source of current available to the system is going to be via the battery and 2 amp voltage regulator. Most USB cables do not provide much more than 500 milliamps at tops. This, and we'll elaborate a little bit more on that here in a minute. This outer row of male pins, okay, these are all going to be ground pins. They are all tied together commonly underneath. And this entire row of pins, sockets, female sockets, are also hooked directly to the I/O. If you looked carefully at your board before you solder it, you'd see a little jumper wire that goes from, for example, right here to right here. Okay, it is important to note that pins 12 and pins 13, they don't have a female socket here. Okay, they've been displaced down here. So this is the female 12. And this is the female 13. Going to this side of the board, it's pretty much the same layout. Okay, this entire inner row of male pins are directly connected to the I/O of the teensy. This center row of pins, male pins, is going to be hooked up to the power supply. These are going to be your voltage out. They are selectable between 5 volts, which is coming via either the USB or the voltage regulator, or by moving this jumper to the lower position here where it says VN, it'll be powered directly from the battery pack. So whatever's coming into the voltage, whatever voltage is coming into the battery pack is going to be then powering this center row of pins. This switch, as I said at the beginning, turns on and off the center row of pins. This is the row you're probably going to have things like motors hooked up to. So you can turn the switch off, and you can do all your software, your programming, check your sensors, everything else. And then when you're actually ready to have your robot move, you simply flip the switch to the on position and it powers up your motors. So it becomes a really handy way of doing your uploading and downloading, testing, and diagnosis without actually having to worry about your robot dropping off the table. The outer set of male pins are going to be a common ground. And once again, these sockets right here, from this one to this one, are all going to be hooked directly to the I/O. So this will be where you would insert a wire, for example, if you want to hook up to your individual pin. These two female sockets up here and these two female sockets right here are hooked up to power and ground. The outer one, on both cases, okay, which lines up with these other females, is going to be ground. The inner one, all right, in both cases, is going to be tied in to the center row. So if you have this set at 5 volts, that means that this inner female socket right here will be 5 volts, and this one out here will be ground. All right. So if we plug this thing into the USB, notice that right now the switches are both in the off position. Okay. I'm going to plug this, I'm going to turn it on, even though there's no batteries, and of course nothing came on because there is no batteries. But you'll see that you can't physically plug in the USB cable. That is because I do not want anybody running their system off of batteries and having hooked up to motors or whatever else, and then at the same time have the power on and plug it into your USB. It might become possible then to feed a back current back to your computer, although unlikely, it might be possible. So you have to turn the power off. I plug in the USB and the system goes live. Okay, this switch is essentially non-functional when the USB is in. It is currently running, it is currently powered up, and all of these pins on this side are currently charged. If I should say the center row of pins are all charged at 5 volts, which is where it's at. If I turn this one on, you can see this light goes on, and currently with this jumper set here, this is at 5 volts. All right, let me show you this. If I move this to VN, power goes off even though I have the switch on. Well, that's because I don't have a battery hooked up. Okay, so there is no alternative source of power. So I'm going to put that back to 5 volts. And let me pause this and get set up here with a couple more little things. Alright, so let's actually hook up a battery pack to it real quickly here. And I'm going to plug this in right here. Now, I've turned this power off. And recall when the last time I turned this, well, if I turn this on, okay, no problem. Power goes on. It's set at the jumper is set in the 5 volt position. This time, however, if I move this jumper over here, you can see that I once again do have power because I do have a power pack, and I'm currently running. These are 6 1.2 volt batteries, so I'm running about actually it'll end up being around 7.6 or 8 volts that you'll measure. Coming up the center row of pins, okay, because we're running it off the battery pack. I will now unplug the USB, okay, and you'll notice that this light is off, all right, the system power is dead. I can turn off this side, which now turns off everything. Everything is dead. But I now can turn on this power, and you can see that the system is currently on and is running off of the battery pack, and it's going to be powered by this 5 volt regulator. So it's set at 5 volts. We should measure 5 volts here. Okay, so let me zoom out a little bit and let's play with these digital voltmeters. Digital multimeters. Okay, I'm going to rearrange things here a little bit for us. And let's explain a little bit about those DMMs. You'll probably use these quite a bit. They're really handy for diagnosing your circuits and figuring out what's going on. Both of these are multifunction. Okay. In this particular case, we have a bottom of the line, very affordable multimeter, and it's got some basic blocks here that you can set the dial to. The ones we're going to be most interested in are going to be measuring DC voltage, okay, which is what we'd use to measure, for example, the voltage of a battery or a battery pack. We're going to be interested in the resistance or the ohms, and we're going to be interested in measuring current. Okay, so current would be the measurement of the number of electrons that are flowing past a particular point. You can measure that as in amps or milliamps or microamps. Resistance is going to be the resistance to the flow of electrons, and we're going to be measuring resistors, which we're going to be using. In fact, your motherboard, you may recall when you built it, has two resistors that sit below this chip that regulate the flow of current going to the LEDs so they don't get so bright and burn out. We don't burn out our batteries. And of course DC voltage, which is going to be the potential between 2 points. And if we look at this meter, okay, you notice this one we have to actually set a scale. We got to be a little bit careful, and we're also going to have to interpret the data that gets displayed depending on the scale. A meter like this one auto scales. There's only one setting for voltage, there's only one setting for resistance, there's only one setting for current. And it's going to auto scale and figure out, and we'll see in its display here what the final values are. Okay? So that being said, let's actually just use the cheap meter, in part because it's smaller and it fits nicely onto the screen. Alright? And what I want to do is confirm that in fact we're getting 5 volts like we expect. So I'm going to use this red wire. I'm going to plug it anywhere in that center bus. So I'm in the center row of pins. I'm going to take this black wire and I'm going to plug it on any of the pins. They're not even lined up here in this case, okay? But any of the outer pins, these are all common ground. I'm going to switch this over. I'm expecting a voltage, less than 20. Okay, so this is probably the scale that I'm going to want, because like I said, I'm expecting a 5 volt supply. I'm going to turn it on, and I'm going to take and measure. Let's see if I get that there, and then the black one. Okay, and I'm getting 5.08 volts, all right, which is quite a bit different than what I'm feeding it. If I take this thing and unplug it, and I take this and measure the outer rim, which is cooked ground, and I'm going to stick this on the inside, which is positive, you can see that I'm actually getting about 7.78 volts. So this device right here is taking 7.78 volts and stepping it down to its 5 volts over here. Alright, I'm going to move this jumper to 3.3 volts, and hopefully you'll see that if I hook this up to, take this wire here, hook it to ground, hook this one up here, we are in fact at 3.3 volts. Okay, and like I said, if I go to this side, I'm going to turn the power. Well, I'll plug this in first. I'm going to plug this into any of the outer row of pins because they're all common ground. I'm going to take this wire and plug it to any of the center row of pins. Okay, these are going to be the supply. I currently have the jumper set at VN, so we would expect it to be, when I turn it on, the same voltage as the battery pack. So if I take and hook this up here, hook this up here, lo and behold, I get 7.74 volts. 7.75. I dropped a teeny bit, but it's probably because the battery pack itself is stabilizing. Let's go ahead and put this on 5 volts. And I guess I'm hoping you know what to expect. Okay. Okay, so you've seen how the motherboard can regulate power and how the switches and settings all work to be able to control its flow and its direction and where you want to hook things up. Now let's actually use the motherboard as a power supply. Okay, and then we're also going to talk about at least one more function with the multimeter. Specifically, we're going to talk about measuring resistance this time. So, before I begin, I'm going to talk briefly about the breadboard. The breadboard is a really nice tool that we can use in electronics that allows us to build temporary circuits and test them and play with them in a variety of different ways. What you need to know about it, though, is that although there's lots and lots of holes, they are actually connected below the board. If we were to peel off this back, in fact, if you look at yours, you can see these bumps that actually make up little metal bands. Okay, there are long metal bands that run underneath here, and there are several metal bands that run along here that make these bump patterns in the plastic. So if we look at it on this side, what we actually have going on is the entire set of holes that are along the red strip are actually connected underneath. So something plugged into this hole will also be automatically connected to something plugged into that hole, or that hole, or that hole, or any hole along the red strip. Likewise, the blue. Okay, anything that's plugged into, for example, this hole will automatically be connected to anything that plugs into this hole or this hole because there's a big long metal strip that connects it underneath. In this case, it goes the other direction. Each group of 5 is connected, so anything that's hooked up to, example, anywhere on the one here labeled 5 in my board, anything that's connected to here is automatically going to be connected to there. So let me just make that clear. If I plug something in, for example, here, all right, and I've plugged that into this pin here labeled on column 20, and I plug something else that's here, okay, these two wires are now connected. Okay, so if I move this and plug the other end over here, I'm just doing this at random, so now I have a connection from here through the metal band in there, comes out this hole over to here, and I can plug something else, for example this LED, and I've plugged it into the same column as this one. Okay, so now it has a path over here, so we can build these little bridges, and we can bridge it all the way across in a number of different ways. So you can build a circuit without actually using wires. All right, so I'm going to start right off by actually taking my black wire, and I'm going to plug it into this blue one here, this blue set. So now these are all connected. Okay, and I'll just put this one in the red. So now what I have here is I've built myself a powered bus. Okay, so anything that's plugged in to this red wire here, or this red bunch of holes, is going to get the power from the power supply, and anything that's hooked up to this column of blues is going to be then hooked to the common ground. And actually what I'm going to do, I'm just going to turn this off, and I'm going to move these over to here. Alright, so I'm going to have it set on 5 volts. Okay, so I'll turn off the power for the moment, but when I turn on this power, I'm going to be getting 5 volts out the red wire. It's going to go to the red bus, and then of course black is going to be back to ground, so I can build a circuit in between. So let's start off talking about a resistor. Okay, so a resistor, well, it resists. Okay, and there are a number of different types of resistors. I can get them in any one of sets of resistances and able to handle any one of a number of different currents. These little guys here that we use are 1/4 watt resistors. They can't handle a whole lot of current, but we can choose any basic resistance that we need. They are actually color coded, and you'll see these things laying around the lab, which we can use to read the resistance. I think it's oftentimes best to start to orient yourself. There's one band at the very end. It's going to be either silver or gold generally. That's a good place to orient yourself. That tells you the quality of the resistors, the tolerance of how close it's going to be to the right value. And then there's typically in the resistors that we're going to see in our lab 3 bands. So if the first band furthest from the gold or the silver is black or brown is pretty common, it would be a 1. Okay. If the second band, like it is in this case, you probably can't see it, it's a brown, black, orange, we would find out it is 1, 0 times a multiplier. Orange is 1,000, so 10 times 1,000 or 10,000. Alright, so that's 10,000 ohms or 10K. So let's go to the meter. Okay, let's confirm it. We're going to have to choose resistance in ohms, and we're going to set a scale which we think is appropriately close, at least. Actually, I'm going to throw it off. I'm going to put it down here like, oops, I don't know what the heck I'm looking for. I put it on a 2,000 ohm scale and turn it on, and let's just measure this resistor right here, this one we know to be 10K. And you know what I'm going to do, I'm going to stick these into 2 random holes which are not connected, just to make it easier for me to hold on to. And oh gosh darn it, I'm not really getting anything. Well, that's not too much of a surprise. Sometimes you get a little erroneous spike of a number, but I'm on the wrong scale. There we go. 9.97K. 9.97K. I'm on a 20K scale, so that's 9.97 thousand or about 10,000. Okay, so I'm within that tolerance listed by the resistor. Let's look at this one. I'm not going to tell you what colors it is. I'm just going to stick it in 2 random holes. Oh, got a brief flash here. Getting bogus data. Let's take it up. I got my wire inappropriately spread across there, but it's 27.1 out of 200K, so it's 27.1K. So this is a 27,000 ohm resistor. And we can confirm it with the color band, but actually I know it is true. Okay, so we can use this to measure resistance, and you have to make sure you choose the right scale if you're going to use a meter like this, which has selectable scales. If you don't get the answer you're looking for, you need to dial it in. There should be some range you're looking for. I would start with that one and then work your way till it begins to actually measure the current, or I'm sorry, the resistance that you sort of expect. Let me pull these out of here. Let me introduce this little guy here. Okay, the LED. All right, we've got them already on our board. Light emitting diode. Light emitting diode, it's a diode, which means it actually only allows electrons to flow in one direction. And when those electrons do flow, we'll get the LED to light up. They do have an orientation. Typically, when you're getting a brand new one wire is longer than the other. The longer one is the anode. Okay, the anode is the one that will be hooked to the positive side of the battery, the positive side of the voltage. And the shorter one, the cathode, would be hooked to ground. Okay. Well, it turns out you can't just plug one of these guys in. If you do to a 5-volt supply, it'll just burn out. All right. So we have to actually provide it with a resistor, and we'll get into the circuit in a little bit. What I'm also going to do, let's just take what resistor do I have? A 10K. That's going to be pretty dim. Let me show you something else. I kind of scattered this. So the resistor, we can get resistance either in fixed ones, like this, okay, which is a fixed resistor, or we can have things that have variable resistance, like this photoresistor. This photoresistor, it changes the resistance depending on the amount of light. All right. I will come back to the LED, don't worry, I skipped a little bit out of sequence. So if I hook this up, you can see that as I darken it and lighten it, we get changes in resistance. Alright? That's a variable resistor, a photoresistor. We can also have resistors which are like this. Okay? In this case, it's a linear sliding resistor. And what you literally have in here is 2 wires, in this case hooked up. On the length of this is a long coil, okay, and there's resistance in this coil from one end to the other. This slider is like an escape path. So if the escape path is very close to where the electrons are coming in, it's very low resistance. It's only traveled a short ways down the wire, and the resistance is very low, and it can flow out wherever this contact is in the length of the coil. As you move it further and further and further and further, okay, you actually go longer and longer and longer along that resistive coil, and the resistance goes up. Okay, so this is a variable resistor that allows us to get a linear motion. There's another one which is very common, okay, and it works on the same way. This is a pot, a potentiometer, and inside of here, if we could crack it open, we would find that there's a coil that wraps in a semicircle all the way around here, and then there's a little metal dial that rides on top of that coil. And as I turn this pot, right, I do the same sort of thing. I allow an escape point on the length of that coil. So if I measured the resistance from one end of the coil to the other, I would find it has, in fact, maybe we'll do that, well, it has some value, like 10,000 ohms. Okay, and then this is my little rotating escape path. So right in the middle, if it goes, the electrons can travel through this twisted coil. They only have to go halfway before they escape. So you might only have 5,000 ohms of resistance. As I get really, really close to the entry point, the resistance is really, really low. It only jumps onto the wire and it jumps right off. Okay, and as I move it further and further away, the longer it has to go through that twisted coil of resistance, and the higher the resistance is going to be. So I'm going to use this potentiometer and quickly build a little circuit. And I think I'm actually going to pause it while I build it so you don't have to actually watch it, and I'll explain it. Okay, so I've tossed together this little circuit here, and I've turned the power on, and you can probably see the light is dimly glowing here. So what's happened, I've got my electrons, my voltage source coming up, going to this common red bus. I have this little yellow or red jumper, which jumps to, I'll pull this out for the moment, the first of these three wires, on the pot. So it goes into the coil. The middle wire is the middle wire of this pot is the escape path. So I've got that hooked up to the anode of the LED. Alright, so I plug this back in. Alright, so whatever electrons manage to escape the escape path go into the LED, and then they come out the cathode, and the cathode ties to the common ground, which then completes the circuit. And as I said, if I turn this potentiometer, you can see that as I get more and more counterclockwise, all right, it gets further and further from that entry point for the electrons, and the resistance goes really high and gets so high that the light goes essentially black. As I turn it counterclockwise, I now move closer and closer and closer to the entry point, and more electrons can escape. The resistance is less because I'm shorter distance on that twisted coil, and of course the light gets brighter and brighter and brighter. Now what I don't want to do is turn it all the way counterclockwise such that the escape is right there at the entrance, because if I do that, it's likely I'll put too much current through and I'll pop that guy. What the heck? Let's just see what happens. I'm going to try it. There's a good chance this will burn out. And, well, I'll be darned. It actually can handle it. I was actually hoping for a little magic smoke there. You didn't get so lucky. All right? But you don't want to be doing this typically, because you could actually burn out your electronics and potentially damage something. So, that being said, I'm going to end this, and I'll see you again here shortly.